So in this video I'm going to talk about the characterization of trees in terms of unique path between vertices. So as a reminder, a tree is a connected graph without cycles. So this is a definition, and the main theorem that I'm going to prove today is that a graph has a unique path between any two vertices if and only if it is a tree. So the statement holds in both directions. So we are going to prove it, and let's start. So proof. So let's start with the direction this way. So here we suppose that the graph has a unique path between any two vertices, and we need to prove that it is a tree. So let's write this. So suppose that our graph G has a unique path, unique path between any two vertices. So we need to prove that it's a tree. So first, if there is a unique path between any two vertices, then there is any path. Forget that it's a unique, but just the fact that there is a path. From the fact that there is a path, it follows that the graph is connected. So because there has any path, it follows that the graph G is connected. By definition. So let's write this. So there is any path between any two vertices it's better to write there is some path. There is some path between any two vertices. Therefore G is connected. Okay, so now we need to prove that it doesn't have any cycles, because the definition of a tree is that it is a connected graph without any cycles. So now we prove it by contradiction. So suppose for cycles, we prove it by contradiction. by contradiction. So suppose that there is a cycle. Suppose that we found a cycle. So let's draw this. So we found a cycle in our graph. Now, this means that between any two vertices, let's pick any two vertices in the cycle, let's say this and this, then it's obvious that there are two paths between them. So one path is like this, and another path is like this. So by going through different sides of the cycle, this way and this way, we see that there are two paths. So pick any two vertices in the cycle and there are two different paths between them by going through through different sides of the cycle. By going through different sides of the cycle. Okay, so this is a contradiction. This is a contradiction. This contradiction with the condition that there is a unique path. So we suppose that there is a contradiction with this. We suppose that G has a unique path between any two vertices, and we found two vertices which has two different paths, which is a contradiction, which proves the one direction of the theorem. So we proved that if G has a unique path between two vertices, then it is a tree. So this direction we proved. So now the other direction, so suppose that we have a tree. Suppose that G is a tree, and we need to prove that there is a unique path between any two vertices. So we are going to prove this also by contradiction. By contradiction. So suppose there is suppose there are two vertices two vertices u and v. U and v such that between them there is a not a unique path, such that the number of the number of paths between u and v is not equal to 1. So it's not unique. So we have several possibilities. So first, this number could be 0. So if this number of path is equal to 0, then this means that there is no path between u and v. If there is no path between u and v, then u and v belong to different connected components of u and v, and so therefore different connected components of g, and so therefore g is disconnected. So g is G is disconnected. This is a contradiction with the fact that it's a tree. So because a tree is a connected graph. So a contradiction so this case is finished. So the remaining case is that the number of paths is greater or equal than 2. So it's not equal, the number of paths is not equal to 1. So that's what we get. The number of paths is not equal to 1, and there are two possibilities. Either it is 0 or it is greater or equal than 2. So 0 doesn't work. So if it's greater or equal than 2, then okay, so now we consider the case when the number of paths is greater or equal than 2. So the number of paths between u and v is greater or equal than 2. So we notice that then between the vertices u and v, we have basically two paths. So the problem is that it's not necessarily a cycle. So because these two paths, they could intersect each other even multiple times. So even something like this. So but what we have is, so this is path P1, let's say, and this is path P2. But what we do have is a closed walk. So this is a closed walk. Closed walk, we start at U, then we go along P1 to V, and then we go along P2 to U, back to U. So this is a closed walk, but it could self-intersect multiple times, and so it's not necessarily a cycle. So now basically the only thing that remains is to convert somehow the closed walk to a cycle. This is not very difficult. So let's formulate it as a lemma. So if there is a closed walk in a graph, then there is a cycle. If a graph contains a closed walk, then it contains a cycle. So to prove this, we simply we go along this closed walk. So let's say that we have this closed walk. Something like this. So we start at some vertex, let's say at vertex U, and we go along this path, along this closed walk, and until we encounter for the first time a vertex that we already visited. So start at some vertex, any vertex, and go along the closed walk until we encounter for the first time vertex that we already visited. So when this happens, this would be a cycle. So this would be a cycle. So first, why this will happen at all necessarily? Well, because we have a closed walk, so sooner or later we will eventually we will come back to the original vertex from which we started. So there is no way not to visit any vertex that we already, also because we have a finite number of vertices in the graph, so we can't go forever without visiting vertices that we already visited. So so for example on this picture, so if we start here from the vertex U, so the first time that we encounter a vertex that we already visited would be here. So this would be the vertex. And then the cycle would be this one. This would be the cycle. So we need to more carefully state what this means. Not this would be a cycle, but the cycle from this vertex that we encountered, from this vertex along the path that we went, to this vertex again. So this would be the cycle. Yeah, so basically this concludes the proof of the lemma, and given the lemma, this concludes the proof of the statement, because so to remind, this was the last case that we needed to consider for path. The number of paths is greater or equal than 2, so we pick any two of them. These two paths combined form a closed walk, like this. By the lemma from the closed walk, we conclude that there is a cycle. There is a cycle, and this this would be a contradiction to the assumption that G is a tree. So, because there is a cycle, this is a contradiction. So let's write this more carefully. There exists a cycle, therefore a contradiction with the fact that it's a tree. A contradiction with the assumption that G is a tree. Yeah, so, and this contradiction concludes the proof of this direction of the theorem, and concludes the whole theorem. So that's it.